very careful about one's language. Remainder. Okay. So there's a number of things that go into this. So I'll first describe. I already stated the theorem last week, but I'll remind you again of what is the variant that he actually proved. There's some work to be done to check that this variant is sufficient, but it's not so impossible. So I guess I'll at least erase one of these to have it ready when I'm done on the other side. Okay, so I think this I can now hide because there's no problem. I mean, I don't right now. So more precisely, so there's a number of things that needs to be done. So first of all, and here I guess the way I define things, I should first put the maximum. So that's the most naive way to write things. So first of all, if you remember the proof of James, that's just a generalization of this, so you can look at your notes and see how this type of error term arose. You don't need an absolute value. I mean, of course, if you can bound with the absolute value, you're in good shape, but you don't actually need it the way the thing comes up. But then maybe you need something a bit more precise than just estimate, but that's not a problem. You will just have some maybe unknown arithmetic functions but of sizes that you control. You don't need the maximum over all residue classes. So we don't need quite absolute value of delta lambda. You don't need all A mod Q, co-prime with Q, but only those which are roots of this polynomial, this function of n which arises here, modulo Q. A such that A plus H1, F plus HK, 0 mod Q. And so typically this will be, because Q is square free, this will be just K to the power the number of divisors of Q. Okay? So if Q is a prime and large enough, then the HIs are distinct mod Q, so you get exactly K roots, and for every prime you get K different roots, and Chinese remainder theorem tells you that that many. So that's K to the omega of Q, which is certainly less than Q to the epsilon for any positive epsilon of such A. So that's quite nice in the sense that, as I'll explain later, this number is not out of reach of the type of techniques that were available to Zhang, but we don't know where these A's are. They could be located anywhere, and so we cannot say that A is small. So if all the A's had been as small as the number of them, that would be much better. Okay. And the third thing is much less obvious. So the fact that you can take A to be that just follows from the method immediately. Much less obvious is that you can assume that Q runs over smooth numbers, so more precisely, arbitrarily fiable numbers. Always square free. I. So this is not obvious. This is the type of things that experts in field theory were kind of aware of, and that suddenly was explicitly noticed by Motohashi and Pins a few years after GP1 came out, although they couldn't exploit that observation. So if you remember, you can kind of have a very vague guess that something like this might be true. If you remember the way the thing came, the Q is not really a fixed Q. It's always going to be the least common multiple of 2 of these R's in the cell box sieve. So this Q will always have at least one factorization. And now if you could arrange a factorization to have many prime factors and so on, you could hope to get something like that. So if you just take this naive observation of cell box Eve, you just know you have one factorization, and you could try and exploit the two variables R1 and R2. Typically, this is not flexible enough, but at least it exists. Okay? All right. So the outcome is that it's enough to go beyond the Bombieri-Vinogradov theorem when you have this type of restrictions. So the following result suffices to get bounded caps. That's the same theorem I stated on Friday, but I will restate it again. This is the strong. This is the kind of slightly stronger version in the Polymath A project, and it goes as follows. So we have. So for any saving power of log that you want, for any positive epsilon, for any non-zero integer, so you sum over Q square free less than or equal to x to the 1/2 plus 7 over 300 minus epsilon. Okay, I got my multipliers wrong again. I need there exists positive delta such that so Q is coprime with A and Q is X delta smooth, so friable. And in fact, you can put the absolute value. So this first observation somehow is more like a psychological thing. It's more the fact that you can take friable integers that's crucial in this argument. So I'll just write it this way: psi of x qa minus psi of x over phi of q is less than x over log x to the a. Okay, and here it's very important, this depends on epsilon, or it may depend on epsilon, on A, and on whichever choice of delta. There might be more than one choice of delta for a given epsilon, but it does not depend on small a. This is uniform in terms of, that's the crucial thing for the application to the GP1 now. So this is significantly weaker. If you allow the implied constant to depend on small a, it's significantly weaker than results of Fourie-Vagnette and Bombieri-Friedlander-Vagnette. But of course, for the GPY method, that's the key thing, that you need to be able to have a uniformity in A. Okay, the 7 over 300 has no meaning. Any strictly positive number instead of 7 over 300 suffices. Zhang's work was something like 1 over 1,200 or something like that. And he certainly did not try to optimize anything, so the fact that this is significantly better represents a certain amount of work, but it is not a crucial feature of the work. Okay? Now I'm going to. There is one of these without getting it too wet. Okay, so we have So what are some of the steps? So I'm not going to be able to give you even anything that remotely looks like Bin-Sync. I just want to try and point out some of the key ideas and some of the key features, like in particular, why can we hope to have things which work for NEA? Why is it unrealistic at the moment with these methods to try to put a maximum over A? This is not known. What is it that one gains by restricting to sufficiently smooth moduli? So this is things I'm going to try and explain, but certainly from what I'm going to say, you should not get the impression that this is easy or that I've explained most of the work. So some key steps. Okay, and many of these key ideas are exactly the same as were found by Fouvry-Ivagnetz and Bombieri-Friedlander-Ivagnetz. Somehow just there are some key observations of Jean that allowed him to detect that this was the key type of statement and to prove it using some of the same steps as Fouvry-Ivagnetz and Bombieri-Friedlander-Ivagnetz, but going beyond what they had been able to do. Okay, so the two steps that I'm going to describe. So the first one is kind of classical. It's the same step as described by Sound in the proof of the Bombieri-Vinogradov theorem. We try to exploit multilinear or bilinear decompositions of the Von-Mangolf function. Multilinear decomposition. Okay, so it's not easy to make things work with the type of bilinear description that Sound explained. I mean, one of the things that the Polymath project realized that, in fact, it could have been done a posteriori, but apparently you need more flexibility. I mean, in Jean's work, he needed more flexibility. So